Hello everyone, my name is Abul Fazl Mahmoudpour, and in this video we are going to solve nonlinear Poisson equation using numerical method and utilizing finite difference technique. Why nonlinear Poisson equation? Because this is a type of equation that you see frequently in semiconductor physics and plasma physics. So let's start. Okay, we have the Poisson equation here, and it is second derivative of v with respect to the x equal to the minus q divided by epsilon naught multiple to the rho. V here stand for potential, x stand for the position, and the q is elementary charge, epsilon is relative permittivity, and epsilon naught is vacuum permittivity. Rho here is indeed the charge density. Let's assume that the charge density contains two terms. One term is n1, that is constant, and the other term has such a form, exponential form. If you notice, you see that this exponential form have potential at each argument. That's why this equation is nonlinear, because right hand side of Poisson equation has the exponential form of the potential. Okay, we have this differential equation, and indeed, because we know the value of the potential at the boundary, our problem is a Dirichlet boundary problem, and we know that the value of potential at the left boundary is some number. I define it with VL. At the right, it is some another number that I define with V right. Same equation, and just for simplicity, I decompose this equation into two terms, and I define this term with some nx. Therefore, this equation will be like this. And in general, what do we do when we want to solve a differential equation using finite difference? The first step is that, okay, we need to discretize our domain into some grids. Instead of having some continuous variable x, we need to have some discontinuous grids, and each grid can be represented by some index that I defined here with I. And the second step is that we need to discretize the differential equation. What is the discrete form of this differential equation? What we need is just remember that the second derivative of the definition of the second derivative using a finite difference is following: vi minus 1 minus 2vi plus vi plus 1 divided by delta x. And this vi minus 1, vi plus 1 are the value of potential at this grid. And the right hand side is very simple, and what I did, just I defined this parameter with a. Okay, and the discrete form of this equation will be following: ni equal to n2 exponential of vi divided by v thermal. Here v thermal indeed is the thermal potential, and we know that that is definition of thermal potential is KT divided by Q. And what I did here, I just replaced x with I. Again, for simplicity, I replaced this delta x with h, and I have this equation by multiplying both hand side of this equation into h squared. We will end up with this equation. And how we can solve this problem? We can solve this problem just grid by grid. How? We know the value of the potential at the left boundary. Okay, then we need to solve this equation for the neighboring grid, and so we need to keep vi at one hand side of this equation, right, and all the other term at the other side of the equation. Therefore, we will end up with such equation: v of is half multiple to the vi minus 1 plus vi plus 1 minus h squared multiple to the a multiple to the n1 minus ni. Okay, we have the same equation that we had in previous slides, and if you notice, you see that vi depends on the neighboring point. It means that the value of potential at this grid point depends on the value of the potential at the left and at the right. Okay, we say that we need to start from the first grid, but we know the value of the first grid from the boundary condition. We go to the next grid. Next grid is 2. If we substitute 2 instead of I here, we will have v1 here and v3 here. We know the value of the v1 from boundary condition. What about the value of v3? We do not have any solution for the other grids except then the first grid and the last grid. So what do we need to do? We need to have some initial guess, right? We need to have some initial guess and use this initial guess in this algorithm that is shown in this chart. Once that we have a V as an initial guess or as a trial solution, we save this V in some V old. We will need this V old. Then by having this initial guess, we put V here and calculate N. After calculation of N, we put this N here and calculate the Poisson equation, because now we have some initial guess, therefore we know the value of potential at every point. Therefore we can use this equation to find the new V at each grid, right? Once that we found the new potential, we need to compare it with the initial guess that was V, right? Now we updated this V using the Poisson equation. If the difference between the new solution that is V and the old solution is less than some small number, we can say that, okay, with some tolerance, our solution is correct, because the difference between our initial guess and the solution that is obtained from Poisson equation is very small. And how we define this small number? We just define some tolerance. What we say that, okay, if the relative error of the potential is less than some tolerance, although the absolute value of the relative error is less than some tolerance, therefore, okay, this solution is acceptable and the solution is final. Otherwise, we need to repeat the same procedure. How? Now, we need to give this V that is calculated from Poisson equation to the V old. This V old logically should be closer to the final solution. Why? Because we had some very rough initial guess, we guessed to have some V. But at the second step, we calculate the V from the Poisson equation using this initial guess. Therefore, the new calculated V that comes from Poisson equation logically should be closer to the final solution, because it's the result of calculation of the Poisson equation. Therefore, by repeating of this loop, we can hence this potential, this initial guess toward the final solution, and reduce the delta V to some small value. Then when this is less than tolerance, we are happy, and we can say that the solution is final. And what else? I think, okay, we have the equation. We need to define some grid number, we need to define the parameters, and we need to calculate this equation inside this loop. Therefore, we need to implement this algorithm and this equation into some code. I will use MATLAB for writing of this code, but you can use any software because what we need here is just some basic calculation. Okay, I have MATLAB open here, and I have the written code here before in order to make video short, and I will explain line by line about every command. I usually start with CLC. I think you know that this is a MATLAB environment. I think there is no need to introducing. We start with CLC, and CLC clear this command window, and clear command just clear the cache, and close all, close every opened figure. Therefore, we have some parameter, constant parameter. Q here is 1. Why I define it to be 1? Okay, just let me write the unit of Q, that is elementary charge here. Sorry, not 1. This is the elementary charge E. When I define Q to be E instead of Coulomb, I should be careful about epsilon naught, but I know that the value of the epsilon is about 55, 26, 34 point some number, and the unit is just electron squared divided by electron volt divided by centimeter, right? You can Google it and you can find relative permittivity in this unit in the internet. And what is epsilon? Epsilon is relative permittivity. It is unitless. Let it be 12, and this is close to the silicon relative permittivity. What we defined some A, and A was just minus Q divided by epsilon naught epsilon. Yes, remember, you remember it here. We defined A. Yes, here. This is the same A. And what we have, we need to define the D. Let it be 4e minus 4. And when this is 4e minus 4, the unit here should be centimeter. Why? Because 4e minus 4 is about 4 micrometer. When we use centimeter here, this unit also should be centimeter. Therefore, this value is just 4 micrometer. And I defined left boundary condition or left value for potential to be minus 0.1, and dimension of this one is volt. And also I defined right boundary condition to be minus 0.4. Again, unit should be volt. And we know that the thermal potential, that is KT divided by Q, is about 26 milli-electron volt. Therefore, for thermal potential, the unit is also volt. And I define the number of grids to be 100. You can choose any number. Just let's start with 100. Therefore, x should now I need to change x from 0 to b linearly just by n number. It means that I divided this d into 100. Into 99 interval. What will be delta x or h? X or delta h will be this d divided by n minus 1, right? And let's define some number for n1 and n2. Just there are some number. They have some physical background, but let's forget about the physics and just focus on the mathematics. Therefore, I defined n1 to be 1e14, right? 1e14, and the dimension of this number should be centimeter squared, 1 over centimeter squared. Okay, and also dimension of this n2 should be the same. I just copy it here, Control C. Control V. If you notice to the equation, indeed this N1 represent the doping density in semiconductor physics, and this N2, if you are familiar with the semiconductor physics, this N2 is nothing but the this N2 is nothing but the effective density of state for conduction band or valence band. That's why their number is their number is logical. For example, 1e19 could be logical value for the effective density of state. Now we say that we need to have initial guess. Very rough estimation could be 0. Imagine that the potential everywhere is 0. You can define some array with zeros command, and inside the parentheses you can define the dimension of this array. This is just a linear array, and the number of columns is n, that is 100, right? But we say that we know the boundary value, and therefore we need to substitute the V1 first grid and the last grid with the boundary condition that we know, and V1 is VL and Vn is Vright. Stand for V left and V right. What is this? This is iteration number. This it underline num stand for iteration number. We didn't start an iteration, therefore I define iteration number at the beginning to be 0. Then I am defining another array. This array, the value of this array is 0, but the dimension of this array is opened when you do not write anything in the parentheses. Therefore, later you can assign any dimension for such an array. I define such a thing to store iteration number in some array to be able to plot some parameter, right? And what is error? I defined again some let's say dimensionless array with ones, and the value of this array is 1, but the dimension could be anything. Another error n. Here error n indeed will be the difference between the V old and V new. That's why the dimension of this array should be n1, similar to the dimension of the potential here, right? And I define it with ones. You can define some other number, but it should not be 0. We will see later why. Therefore, it's better to define the error initially to be 1. And we say that if you notice to the algorithm, we say that we need to define some tolerance. And if the relative error is less than tolerance, we can stop calculation. Otherwise, we need to repeat calculation inside the loop. Therefore, here I define tolerance to be 1e minus 14. What does it mean? It means that our desired value for the tolerance is 1e minus 14, and the calculation will stop when the difference between the old solution and new solution is less than this number. And when this number is really small, we can be sure that the solution is true. Let's see. Okay, and here I define a while. I define a while loop. This is the big loop that you saw here. This is indeed the while loop. And I say that, okay, when maximum of error underline a, n. This error underline n show the errors correspond for each grid. Because the number of grids is n, therefore the difference between the old solution and new solution at each grid should be known. And when we are sure that the maximum of this error is less than tolerance, therefore the other error is less than maximum, right? Therefore they should also be less than tolerance. And this command, I define a command here and say that if iteration number is greater than some number, I defined it to be 100,000. If iteration number is greater than 100,000, break the calculation. And this end is for this loop. And here you can print some command like warning or error. And using fprintf, inside parentheses you should write 2, comma, and you can write everything here that you like. What I write here is when this condition is satisfied, when the iteration number is greater than 100,000, print me this sentence: maximum number of iteration is reached, solution cannot be found. And you should to put this backslash in here. We will see how it works. Then the next step in the algorithm is what? Giving the v that we defined as an initial guess here to be 0, here to be 0, giving this v to some v old, right? After that, what is the next step? The next step is calculation of n using this equation. Therefore, once that we know the v, we know the initial v, we can calculate the n, and that is nothing but n2 exponential of v all divided by thermal v or vt. Then I say that, okay, we need to solve Poisson equation grid by grid. This is the same equation that we derived in the slide. If you see, this is half multiple to the vi minus 1 plus vi plus 1 minus h squared multiple to the a multiple to the n1 minus ni. And we need to change I from 2 until n minus 1. Why? As I mentioned, we know the v1 and vn. What we do not know is the value of the potential, let's say in the inner grids, not at the outer grids or at the grids associated to the boundary value. Therefore, what will be the error? We define error to be the absolute of v minus v old divided by v old, right? This is indeed not the absolute error. This is absolute value of this parameter, but this is not absolute error. This is indeed relative error because we define this delta v to v old, and this will be the relative error. But if we do not divide it to this v old, it will be the absolute error. But it's better to work with the relative error, because if you have several parameters, comparison of relative error, which for each parameter is rather simple. Then when we have one iteration, I need to add 1 to the iteration number that was 0. I am increasing iteration number by 1. What is the next? Here I save this iteration number into this array that I defined with dimensionless, let's say non-specified dimension array iteration here. right? I just save the iteration number to this array, right? And then what? I save the maximum of this relative error, absolute of relative error that I defined here, absolute value of relative error that is defined here, to some other array, and this array I just call it with error. That also I defined it here with some unspecified dimension array. And this is the end of our loop. If you look, yeah, and we define delta n, and we define this indeed this value delta v divided by v old. And okay, when this loop start, okay, when this loop start, it says that when the maximum of the error at each grid point, or not each grid point, when the maximum of error at all the grid points is less than tolerance, it will stop. But while this error is greater than tolerance, this loop will be repeated. Okay, and next step is just plotting of the results to see what is the appearance of the potential. And this command is just I plot v versus x and this x. Okay, and I define this x with 1e minus 4 to have a macrometer unit for the x. Here you see x label is x and the unit is macrometer, y label is v, that is potential, and the dimension, then the unit of this dimension is potential is v divided by centimeter. True. And this grid on just plot the grids inside our figure. And the next figure, we need to define next figure. Next figure, I plot the error that defined to be the maximum of error as a iteration. This iteration indeed is iteration number. This shows the color. The plot will be with the red color, and the line width will be with 1.5 grid on. And then I just this command y line tolerance with blue color and dashed line, and the line with 1.5 just will plot a horizontal line inside our graph to show us the defined value for the tolerance. Then I define to be the y scale and indeed y axis and x axis to be in logarithmic scale, but using this command set GCA y scale log, and x label here is iteration number and the y label is error. Okay, now we have the code. You can stop the video and see everything line by line, and now you know what line is for what. Each line is for what. Okay, what do we need? Just now let's press F5. Okay. Okay, just before that, let's disable this command while maximum error is greater than tolerance, and instead of that write a simple loop and change we are going to define the number of iterations. Let it be from 1 to 10 for k. Yes, I forgot the 4. For k from 1 to 10. It means that we now repeat this loop 10 times. Let's press F5 and look at the appearance of potential and the error. Here you see this is the error and this is the potential, and this dashed blue line you see it comes from this y line here, y line, and shows the level of tolerance that we define, and it is in 1e minus 14, right? If we change it to 1e minus, for example, 8, you see here 1e minus 8. You see that after 10 iteration, when we solve the Poisson equation 10 times inside that loop, the relative error is considerable yet. You see, if I can, yes, here show you the, yes, you see the relative error is about 0.053, right? And this is very far from our desired error. Therefore, what we need to do, just increase of the iteration. Let's increase it to 1000. You see, it is still very far from our desired tolerance. Let's get back tolerance to 1e minus 14. You see, and the maximum and the iteration number here is 1000. Let's increase it to 5000. You see here convergence will become slightly faster. We have slow convergence here until, for example, until 461. Then the tolerance is almost constant, but finally it starts to converge at 4390. Therefore, I disable this command and enable this one. And this time it means that I have not predefined for the number of iterations, just while error is greater than 2, this loop should be repeated, otherwise it will stop. Let's press F5. You see, we define tolerance to be 1e minus 14 here, and the relative error when it reaches to this level, the calculation is stopped. And if we zoom here at this part, you see that the error is less than this tolerance, and calculation is stopped there. And okay, this is our convergence index, and this is the appearance of potential. And you see that how is different when we have less iteration. For example, let's have 50 iteration. Control T and disable this command with Control R. When we have 50 iteration, you see the appearance and potential is completely different, but this solution is not correct. Why? Because the changing between new solution and old solution is really far from our desired value for the tolerance. And this tolerance should be in the order of 10 to minus 10, depends on the problem, depends on the physics, depends on the equation. But I think 10 to minus 10 is enough, and you can even choose 10 to minus 13, 14. Okay, but here I choose to be 10 in power of minus 14. Again, I enable this command, Control T, and disable this one, Control R, and press F5. You see the convergence. Okay. What if I change some parameter? For example, what parameter? I mentioned that this N1 stands for doping density in semiconductor physics. Let's increase this number from 1 in power of 14 to 1 in power of, for example, 15, and check the convergence and check the potential appearance. F5. We have converged. I mean the problem is converged, and here you see the graph for convergence. Let's look at the potential, and this potential indeed is true solution. Let's increase it more to 1e15, from 1e15 to 1e16. Press F5. You see, we see some tendency for divergence here, but it's still the problem can converge, right? But here it seems that here it wants to start to diverge, and I think if we increase the this number N1 from 1e16 to 1e17 and pressing F5, you see this is the same command that appeared because of this this command here, right? Not command, this is the same sentence that appeared here because of this command. You see why? What's happened? If you look at the iteration, the convergence, you see that the maximum of iteration that we defined to be 100,000 here, you see, it reaches to the maximum. It reaches to the maximum iteration, but without any convergence. You see that here very strong oscillation appear. Therefore, the solution is not trustable at all. The solution is completely wrong, and maybe you can confirm by looking at the appearance of the potential. And this solution is completely wrong. And I can show you when we increase the n1 number to 1e18, pressing F5. You see, this is the convergence. You see very strong divergence initially, but it's tried to converge, but finally, again, an oscillation started here without any convergence, and here is our desired level for the tolerance. And if we look at the potential, this potential also is wrong. Why? Because we do not have convergence of the problem. So it seems that when this n1 is in the order of 1e14, 15, 16, the program, the code can converge. The solution can converge. But when I increase this n1 to some higher value like 1e18, there is no convergence at all. And the question is there any way to make this problem to be converged? And the answer is yes. I want to show you how we can improve the convergence of problem, and this is nothing but linearization of the Poisson equation. How do we can do such a linearization? Okay, let's go to the slide here, full screen. Okay, you remember this is our problem, this is the differential equation, and this is the definition of n. We have this n. We used some old in our code, and we say that we are trying to make this old to be close and closer to the final solution. And it means that finally, if we have convergence, the difference of old and v should be small. Therefore, the trick is following. We multiply right hand side of this equation with some exponential of v old divided by vt, and divided the right hand side also with the same term, exponential of v old divided by vt. This term, this multiplication of these two terms indeed is 1, because this is positive, this is negative, and the result is 1. And if we rewrite, let me choose laser pointer again. If we rewrite this equation, we will have such an equation here. Just I gather this term and this term in here, and we have v all divided by vt here and n2 here. And we can make new definition, n2 multiple to this term, we can define it with n old. Therefore, n is n old exponential of v minus v old divided by vt. And we know that finally, this v minus v old will be very small, in the order of 1e minus 14, because we define tolerance to be this number. Therefore, we can use the Taylor expansion of the exponential function. We know that the Taylor expansion of the exponential function e alpha is 1 plus alpha squared divided by 2 factorial plus alpha cubed factorial plus higher order term. And when alpha tends to 0, it is very small than 1, we can neglect all the higher term and just keep this 2 term. Therefore, we can approximate exponential of alpha with 1 plus alpha. By applying of this formula in this equation, we can write this as following: n old multiple to the 1 plus v minus v old divided by v thermal, right? Then just multiplying of v old into each of the term, we have 3 terms here. And by substituting of this n in the Poisson equation, the right hand side will be following, right? And if you notice, you see that previously we had the exponential form dependence of the right hand side to the potential, but what we have now is the linear dependence of the right hand side, because you see that we have v here instead of exponential of v. Therefore, we just send this term to the left hand side of the equation, and rewriting on the right hand side, we will end up with such an equation. And when v old is equal to the v that finally should be, this term and this term will cancel to each other, and what is left will be the previous nonlinearized Poisson equation. And just for simplicity here, I removed this subscript old from n. we know that this ends comes from the V all, but I just for simplicity remove this subscript all. Therefore this is the final equation that we have, this one. And what will be the discrete form? If you remember, this is the definition of the second derivative using finite difference technique, and this is the discrete form of this term, a vi divided by vt v thermal multiple to the ni equal to the a v old I divided by vt multiple to the ni plus a multiple to the n1 minus ni. Again, we try to keep vi in one hand side of equation and the other term at the other side, just taking out v from this term and this term, and sending this term to the one side and bring these two terms to the other side. We will end up with this equation, and what will be the vi? It will be this terms divided by this term, and this is the final equation. What is this? This is the discrete form of a linearized Poisson equation. What we need, let's just try this definition inside our loop. Let's go to the MATLAB. Okay, here. What do we need? We need to replace definition of vi here instead of the upper line. Vi should be following. If you remember, we have some numerator, we have some denominator. Okay, numerator, denominator. What we have in numerator is vi plus 1, right, plus vi minus 1. This two term is divided by h squared. What else? We have some minus a vi multiple to the here a vi and I divided by vt minus a multiple to the v old I. It was v old I multiple to the ni divided by vt minus the third term is a n1 minus ni. A multiple to the n1 minus ni. Okay, and what do we have in the denominator is 2 divided by h squared minus an divided by v thermal. 2 divided by h squared minus what? Minus an, a multiple to the ni divided by v thermal. V thermal, not v underline h. Yes, this should be vth. Okay, just another semicolon here. Just let me check. Vi plus 1 plus vi minus 1 divided by v squared. Okay, minus a vn divided by vt minus ev old n divided by vt minus a n1 minus a n1 minus ni, the same term, and we have the same term at the denominator, right? 2 divided by h squared minus a ni divided by v thermal. Okay, I just disabled the upper line with Control R, and now we calculate this equation. Let's try to see, okay, does it work for lower doping density or lower N1 when it has 1e14? Just for comparison, now we calculate the second equation, or in other words, we are calculating the linear form of the Poisson equation. You see that we have a convergence and the solution is the same. And surprisingly, you see that when we linearize Poisson equation, you see what is the maximum arbitration? It's about 3191. But for the upper line, Control T, that is that is nonlinear form of Poisson equation, what is the maximum of the iteration to be reached to the desired tolerance is 7729. So, okay, it works well and it makes the convergence fast. So let's use the linear form of the Poisson equation and check does it work for higher number of n or what when it is 1e18. Press 5. Amazing. You see, the maximum number for iteration is about 12, and just by 12 iteration it reaches to the relative tolerance to be 1e minus 14. You see, just let's look at the appearance of solution, and the solution is exactly true because we have convergence, and we know that when the doping density is high, as I mentioned, this N1 play role of doping density, we will have very strong changing in the potential at the boundary. And if I increase the number of grids, for example, from 100 to 500, you see, pressing F5, I will have the required iteration number increased, but we increase the accuracy of the potential close to the boundary. If you notice, we have such a sharp changing of the potential at the boundary, and again by increasing to 10,000, again we have convergence, and it is the potential, and it works for all doping density. I just reduced n to 100, and you see it works for all different range of n1. We have convergence, and this potential should be very close to the exact solution. Yeah, thank you for your attention. I think that's it. And you see that for convergence we need something close to the, let's say, 3000. In average we need about 1000 iteration to have this convergence, but is there any way for improving this calculation further? The answer is yes, and it will be the matter of next video. Thank you for your attention, and goodbye.